Hi, my name is Samir Desai, and in this video, I'm going to teach you how to assign oxidation numbers to carbons in organic compounds.
It's easy to get jaded in organic chemistry and simply memorize seemingly arbitrary rules. In this case, the rules involved with computing the oxidation state of carbon. But rather than diving right into organic redox, you'll be learning why things are relevant, which will undoubtedly help conceptualize these topics. Oxidation numbers are whole numbers that can be positive, negative, or zero, and the value indicates the number of electrons an atom has. The number chemists calculate are used in redox reactions to determine if electrons are transferred to or from the atom of interest. For example, an atom that gains electrons is said to be reduced, while an atom that loses electrons is oxidized. You'll delve further into this concept in subsequent videos, but that's enough background to learn the rules behind assigning an oxidation number to carbon. If we look at a carbon bonded to two hydrogens, a methyl, and an electronegative atom like chlorine, let's observe how these rules can be applied to determine the oxidation number of the central carbon in purple. The first thing we want to do is assume all bonds are ionic, and instead of drawing it out with the bonds, let's redraw this molecule with two electrons in place of each bond. Electronegativity follows a trend on the periodic table where electronegativity increases as we go from left to right and as we go from bottom to top. So an atom like fluorine in the top right will be more electronegative than hydrogen, since that's to the left of fluorine on the periodic table. Similarly, chlorine is more electronegative than carbon, so the electrons would go to chlorine. I'll make these electrons red to signify they belong to chlorine rather than carbon when assigning oxidation numbers. And in the carbon-hydrogen bonds, carbon is more electronegative, so the electrons will go to the carbon. I'll change these electrons to purple to illustrate carbon has a stronger hold over the electrons than the hydrogen. Next, when atoms have similar electronegativities, the electrons are split evenly. Two identical atoms, like carbon bonded to carbon, illustrate similar electronegativity. One electron stays with the center carbon, denoted by the purple color, and the other electron goes to the methyl, so that electron will be red. The third step can be rewritten as an equation. Oxidation state is equal to the number of valence electrons the atom of interest would be expected to have minus the actual total valence electrons of this particular atom. The number of valence electrons expected is related to the group the atom is in. Hydrogen is a group 1, so it has 1 valence electron. Chlorine, a group 7 halogen, has 7 valence electrons, and the atom of interest, carbon, is a group 4 atom, so it is expected to have 4 valence electrons. The actual number of valence electrons won't be common knowledge. This is where steps 1 and 2 come in to help you determine the actual number of valence around the central carbon. The electrons in purple signify the valence electrons around the carbon of interest. 1 electron from the carbon-carbon bond and 2 electrons from each of the hydrogens means that this carbon has 5 valence electrons. Therefore, the oxidation state will be 4 minus 5, resulting in carbon's oxidation number being -1. In this example, chloroethane didn't have an overall charge, so the sum of the oxidation numbers will total 0, indicating a neutral molecule. Now that we know the rules, let's see if you can apply this knowledge to a question and assign oxidation numbers to carbons in a molecule. Here, you're given ethyl 2-chloro-2-methyl-propanoate, along with the structure, and asked to assign oxidation numbers to every carbon. While it looks like there are 7 carbons to assign oxidation numbers to, notice that some carbons are directly bonded to the same 4 molecules. Let's call this carbon carbon A. 2 carbons will have identical oxidation numbers, this one and this one, because they're bonded to 3 hydrogens and 1 carbon. Continue to label distinct carbons with different letters, then you'll end up with B, C, and D. Starting with the oxidation number of carbon A carbon atom would be expected to have 4 valence electrons, minus the actual valence. The carbon will take 2 electrons from each of the 3 hydrogens and 1 electron from the carbon-carbon bond, giving a total of 7 valence electrons. 4 minus 7 equals the oxidation number, which equals -3. This is a good time for a reminder. Oxidation state is not the same as formal charge. So an oxidation state of -3 does not mean that carbon has a -3 charge. Assigning an oxidation number simply helps keep track of where the electrons are. This will be important in later lessons, so for now let's get back to assigning oxidation numbers to carbon B, C, and D. And each of these carbons would be expected to have 4 valence electrons minus the actual valence that you'll need to determine. Carbon B is attached to a chlorine, which is more electronegative, so the carbon gets no electrons from that atom. It does get 1 electron from each of the 3 attached carbon atoms though, giving a total of 3 valence electrons. 4 minus 3 equals an oxidation number of +1. Carbon C is attached to 2 oxygens, both of which are more electronegative, so it gets no electrons from those atoms. This carbon C does get 1 electron from the attached carbon atom, giving a total of 1 valence electron. 4 minus 1 results in an oxidation number of +3. Lastly, carbon D. The carbon attached to the alcohol portion of the ester has 1 bond to oxygen, so it gets no electrons from that atom. Carbon D does have 2 bonds to hydrogen, so 2 electrons for each of the 2 hydrogens, plus 1 electron from the carbon-carbon bond gives a total of 5 valence electrons. 4 minus 5 results in an oxidation number of -1. Assigning oxidation numbers to carbon is the foundation of organic redox, and you should now feel comfortable with this concept. You should still make sure to follow up this lesson with practice questions until you feel absolutely confident with oxidation states.